Our next speaker is Marc George. Before, I would like to say something, an introduction about Marc. He studied physics at the Technical University in Vienna. Then he obtained his PhD from the Technical University in Berlin for the investigation of the electronic structure of vanadium phosphorus oxide. After a postdoc at the Department of Inorganic Chemistry of the Fritz Haber Institute of the Max Planck Society in Berlin, he moved to the University of Aveiro. Then, in 2010, he obtained the group leader position at the Fritz Haber Institute, where he started to develop and implement tools for in-situ electron microscopy. In 2015, he started to lead a second electron microscopy group at the Max Planck Institute of Colloids and Interfaces. And finally, in 2018, he accepted a new position at the Scientific Center of Optical and Electron Microscopy in Zurich. So, Marc, please, the microphone is yours. You can start whenever you want.
So now it worked. I was still muted, and I will now quickly share my screen. And yeah, first of all, I want to say thank you to Igor and everyone who was involved in the organization for giving me a spot here. Can you see my first slide here?
Yes.
Okay,
yes.
Great. So this works. Yeah, it is. You know, I was looking forward for so many months to come and visit Aveiro to meet many of my friends, and I'm really disappointed about all this Corona thing. But at least you can do it now online. It would be nicer to be there in person and to meet everyone and have some good bacalhau. But okay, we take it as it is. Maybe there will be a future chance to visit many nice people in Aveiro. Okay, yeah, so I will speak about in-situ electron microscopy. It's something that I started in my group a few years back in Berlin, where we actively moved into this direction. It is not an introductory lecture into electron microscopy in general. So I'm really mostly focusing on the in-situ topic. But let me first start about like what is state of the art. So at the moment we have nice equipment, electron microscopes that have improved optics, aberration correctors, and so on. We have super good cameras. We have detectors for energy loss spectroscopy and EDX and elemental mapping and so on. And this is here my daughter, just as a symbol that you have a good sample, then it's easy to take atomic resolution pictures in principle. So we can study at sub-angstrom resolution the arrangement of atoms. And I would say for most applications, the microscope's lateral resolution is really, really sufficient. Not only can you study atomic arrangements in sub-angstrom resolution, you can also visualize individual atoms. So this is like on a carbon support, some zero atoms, and you can really easily see in this scanning mode individual atoms. So we have enough sensitivity to locate even individual atoms, and we can do spectroscopy and analyze what type of atoms are in our sample. And with energy loss spectroscopy, we can even address the chemical state. So, but imaging in vacuum at very high resolution is not all. And I have here this slide that I use as an introductory slide to justify why do we want to go to in-situ again. There are a few issues about electron microscopy. It's actually the perfect tool to learn more and more about less and less until at the end you have a few million times of magnification and you look at a few atoms and then maybe you know everything about one single particle. But this is quite isolated information in many aspects. So you know maybe everything about one single atom, but you don't know much about the surrounding and the context. So let me just show you this example. I take this example because here in Switzerland, Swiss watches are important. Imagine you have like one piece and you study this piece in all detail. Then maybe still you don't know how everything works together in the context. So we have built microscopes that allow better and better and higher resolution. But somehow you get rid of the context because you focus so much into individual details. And one of the things that are important for context is the chemical and physical environment. So what we do in normal electron microscopy, we study with electrons that are very, very strongly interacting particles. We study samples, single atoms and everything. Because the electrons are so strongly interacting particles, that's because that is the reason why we can actually see single atoms. With X-rays, it's not so easy to see single atoms, but electrons are strongly interacting. Because they're strongly interacting, the whole microscope has to be evacuated. Otherwise, the electrons would constantly get scattered with the molecules in the gas phase. So when you want to really do high-resolution imaging and record beautiful pictures, you have to have your sample in vacuum. Now, that is a kind of a limitation, and this also removes your material a bit from the context that you actually are interested to study. Yeah? So imaging in vacuum of isolated systems that are usually at room temperature and thermodynamic equilibrium with in the temperature of the microscope, that can be quite boring. Yeah? So this is really an isolated system. There's not much going on. And in many cases, our research is actually focused on some functional materials, on catalysts, or we want to know how a specific material behaves under given stimuli. Yeah, some temperature, light, whatever. Yeah. And these high resolution machines that are operating in vacuum, they are limited in this respect. And that is why we try to go towards in situ. That means we try to do investigations not in vacuum and ideally under defined stimuli, yeah, temperature, chemical surrounding, and so on. And then when you have this possibility, then you can study your materials under relevant conditions. Like, for example, when you study catalysis, and I will give a talk about such things tomorrow, we can look at the material while it is in a relevant state. And then we can correlate the structure with a specific function of a material. We can get this important structure function correlation much better than if you just look at atom distributions in vacuum. For many cases, I mean, for some cases, it's important to just study the bulk structure of a material in vacuum. But every time you want to see how a material acts with the surrounding, you should actually go towards in situ microscopy. And as I mentioned at the beginning, when you have microscopes that you can really study individual atomic arrangements at a million times of magnification, you learn a lot about very, very small dimensions and small particles, but you lose a bit the context. In order to do some context-embedded investigation, you should not only do high-resolution electron microscopy, but you should also use some other type of microscopy that allows you to embed this high-resolution information into some lower resolution context so that you can relate the things that you see on the atomic scale with things that happen maybe on the micrometer scale. And there are lots of collective dynamics, also some of which I will show tomorrow in my presentation, some collective dynamics that involve the transport of many, many, many atoms, and often also fast transport of many atoms, and things that are related to heat and diffusion, for example. And such processes is difficult to study at atomic resolution. So for this, actually, it is quite a good idea to correlate observations in the TM with observations that you do at lower magnification, for example, in an SEM. And what you see here in this slide is like a comparison between what a SEM can do when you have a special machine for in situ scanning electron microscopy and what you can do with in situ TM. So just first in my talk, I will speak a bit about in situ scanning electron microscopy. These are quite nice instruments. You can buy them commercially. They can operate it in a mode where you can actually introduce gases into the chamber. And yeah, I have here written down the pressure regime. In fact, you can, with some modifications of the vacuum system, operate them basically from the base pressure, which is like 10 to the minus 5 Pascal, all the way up to 1 bar, that's 10 to the plus 5 Pascal. So it's nearly 10 orders of magnitude in pressure. That's quite huge. And then, yeah, when you have controlled gases, here's a gas feeding system that we built here, for example, in the back. You can then control the atmosphere in the reaction chamber. And yeah, in our case, we also have mounted the mass spectrometer, so we can analyze the composition of the gas phase inside the chamber. And you can heat the sample, and then you can study material in a given atmosphere and look at morphological changes, for example. And the good thing is you can do this in such a microscope in the range of like a millimeter. That's the size of your sample. It's in a millimeter regime. And you can zoom in And then a bit depending on the pressure, you can still achieve resolution down to a few nanometers. So you bridge a quite large scale of lateral resolution. And then when things are getting too faint to be seen, then it makes sense to also go to the TM, where depending on what type of setup you have, I will introduce a few in my presentation, but you can, with for example, these special holders for in-situ electron microscopy, you can go up to pressures of 1 bar, up to temperatures of 1000 or even more. And then you can again connect a mass spectrometer such that you can study your materials under a defined gas phase in a given temperature. And while you look at your sample, you can study, for example, in the mass spectrometer, if the gas phase is changing its composition because of some type of reaction that is running. So I would first start with the SEM, and later I will go to the TM, and I will also show a few examples. And I think we're only like 30-something people or 40 people or so. We have enough time, and I suggest if you have any question, just drop a question or send a text message or so, and I will try to immediately respond so that it is most fruitful for you. It doesn't make sense if I talk and you get bored. So just whenever you have a question, just come up with it. If you want to enter the topic and learn about environmental, so that this word here up there, ESEM, is environmental scanning electron microscopy. If you want to learn about environmental scanning electron microscopy, you should read the paper of Danilatos. This is the guy, he's a Greek guy, he's now in Sydney. He's the guy who basically started to play around introducing gas into the scanning electron microscope, and he modified the pumping of the chamber by some differential pumping stages and so on. And so he's really the pioneer, and he wrote a lot of nice papers, and he demonstrated also what can be done with environmental SEM. So because you can introduce gases, you can heat and cool your samples, it is possible to look at like wet samples, samples that are otherwise charging, and so on. So here's just an example. This is a oil in water emulsion, so you can really look at liquid phases relatively simple. You don't need to do much preparation. This is another example, just a picture here of ice crystals. So when you have some humidity in the chamber and you cool down your sample, you can study crystallization of ice. There are also lots of beautiful videos. If you go on YouTube and you just type in situ scanning electron microscopy, there's a lot of material around, and it's really a wonderful technique. So, I would actually advise many people that like to do in situ electron microscopy to really start with in situ scanning electron microscopy. A scanning electron microscope is much cheaper than a transmission electron microscope. It's extremely versatile, and for many things you can actually learn enough. You don't need always to see the atoms, and that is a long topic. I could talk about this forever, but like atomic resolution has lots of limitations, and many people forget about in situ SEM, but it's really a good complementary in situ method. So just a few words about the setup of such an instrument. What you see here is a general, simplified drawing of a normal scanning electron microscope. You have the gun, electrons get extracted and accelerated. They have a condenser system to make a nice small probe that you scan across your sample. Everything is in vacuum. And then you have a number of detectors, and you look at the backscattered electrons and the secondary electrons, and you record your images. When you have an environmental scanning electron microscope, the setup is pretty much the same. Of course, you have again a column where you form your nice electron beam, and the beam flies through vacuum. But just before the beam enters the chamber, you have a differential pumping system. So you have a few apertures. I don't know if you can see my mouse, but you have a few apertures, and the pressure increases stepwise towards the chamber. So ideally, the electron beam that is formed here flies in a good vacuum, and only shortly before the beam hits the sample, it is actually entering a region of higher pressure. So that's all. You just need a few pressure limiting apertures and the different types of pumps, and then you have your environmental scanning electron microscope. So the whole secret is basically really in the way how you make sure that you can allow some pressure in the chamber where the sample is, and how you can still maintain a good vacuum for the optics of the microscope and the filament especially, that is most sensitive for gases because it's usually very hot. And a few things that you need, of course, to consider is when the electron beam that is, of course, focused to a very sharp, small point that defines your resolution, the probe size, the probe at which you scan your sample. You need to make sure that when the beam, the focus beam, enters the gas and there's the surrounding of a sample, that the focus remains somehow. And what happens, of course, when there's gas inside is that the electrons can get scattered on the gas molecules, and then you get actually a distribution of scattered electrons. And the more gas you have in your chamber, the more of the primary electrons get scattered, and only a small fraction of your initial beam really still hits the place of focus. But the good news is that all the scattered electrons, they get really randomly scattered to random positions, and they basically only contribute to a background. It's a diffuse background. As long as significant, or not even significant, as long as some portion of the beam still remains focused, and according to some calculations, even if only 5% of the primary beam is still focused and 95% is scattered, because these 95% just gives background and only 5% come from one place and give a coherent signal, you can still do imaging. Of course, the signal noise ratio gets bad, but this shows you that you can have a lot of scattering but still see something. Of course, when you have more gas molecules, you get more scattering, and at one point none of your focus beam electrons still reaches the sample at the point of focus. But this is important. So you can accept quite a large amount of scattering and still actually see features of your sample. And now a few things about the detection of electrons. So in a normal scanning electron microscope, this is a picture from inside the chamber. You have here the piece of the bottom piece of the column where the objective lens is inside, and the electrons normally come out here from this hole, and they hit the sample that is somewhere down here. And the primary electrons can get backscattered. So up here you usually have a backscatter detector, but the primary electrons also can create some secondary electrons that are lower in kinetic energy. They get sucked to this Ewald-Thurner detector. These detectors you have anyhow, even in an environmental SEM, they're also equipped with these detectors because you can operate it as a normal SEM. But when you introduce gases, then you have to switch off this Ewald-Thurner detector, because this one has here quite high electric fields for acceleration of the secondary electrons. So this one is deactivated, but you switch on another detector. That's this golden plate here in the back. It's called gaseous secondary electron detector because it's used when you have gases inside the microscope. And here on the right side, there's a schematic drawing. Here, this gaseous secondary electron detector is symmetrical around the primary beam. It doesn't matter here, it's just on the side, but it can also be directly under in the central part of the beam. But the function is very simple. You put it on a positive potential. So here it's just really a metallic plate that you put on a positive potential. When the electron beam hits the sample, it induces the formation of secondary electrons. And these negative secondary electrons, they are getting accelerated towards this positive metal plate, this detector. And on their way, when they get accelerated towards this anode, they can hit gas molecules that are in the chamber and ionize these gas molecules. And in this process, create more secondary electrons in the gas phase. And they get also accelerated to the positive anode, and eventually also even excite more secondary electrons through further interactions with gas molecules. So what you have is that a single secondary electron actually can give rise to an avalanche of secondary electrons. And this is actually a signal amplification. So the electron beam hits the sample somewhere, and you create an avalanche of secondary electrons that you can then detect. It's a bit like a Geiger-Müller counter. Yeah? So you have a nice signal amplification. Of course, the signal amplification depends a bit on the density of the gas and also on the ionization cross-section of the gas molecule. So it's a bit depending on the gas mixture. There are some good gases for imaging, and there are not so good gases for imaging. And these gases we can actually call them imaging gases, gases that we put into the chamber in addition to increase the imaging properties. But that's all. The detection is really very simple. You have a piece of a metal, a detector that you put on a positive potential, and you just measure the current. That's your detector. So what can ESEM do? The good thing is, and I should maybe go back to this slide, I'm sorry for that. The good thing is, because you create here, when the electron beam hits the sample, you will get secondary electrons that are getting emitted. And it's often happening when you look at samples that are non-conducting, that they can charge up in the SEM. So for many investigations in SEM, you have actually to coat your non-conductive samples either with a film of carbon or you deposit some metal on top to make them conductive. In the SEM, you have lots of ions. You can easily charge neutralize the sample. So even if your sample is charging, non-conducting, if you introduce a bit of gas, you can actually study them without putting a coating on. This is really beautiful. So even if you're not interested in any in situ studies, if you want to study some, whatever, a flower or a beetle or whatever, you put something in a microscope, it's normally charging up. You introduce a bit of gas and charging is no more issue. So this is really good, and this allows you to work fast without much preparation. And in fact, many tabletop microscopes, these tabletop SEMs, they have this mode implanted automatically. So you can really introduce a bit of gases just to prevent charging of your sample. Because you can play with a pressure range, you can actually work and study with, you can work with wet samples and study liquids even in the scanning electron microscope. This is beautiful if you want to study any crystallization processes, for example. And because you don't need to coat and you can put samples in the natural state into the microscope, you can do interesting experiments. You can, for example, heat up a sample. You can do stress testing and mechanical deformation and all these kinds of things. So it's a brilliant platform for in situ experiments because it offers a lot of space. When you think about a TEM, you have your objective lens and there's not enough space really to put more in between than just your sample. But in a scanning electron microscope, you could put fibers inside for light, you could put an AFM inside, you can, there's so much space. So it's really a perfect platform for studying many different things in situ. Now I have praised this method so much, but I should also tell you some of the drawbacks. Yeah? So whenever you want to do in situ scanning electron microscopy, you have to take what is on the market. So you buy a commercial environmental SEM, and these microscopes are perfect for general usage, but they have the limitations. And one of the limitations that I'm suffering from is the poor vacuum quality. So it is not a UHV instrument. You know, it has normally not a load lock system, and you have just a door that you can open with a huge rubber O-ring. So the vacuum is rubber sealed. And whenever you have some rubber components that is not good for vacuum, you cannot bake out the machine. So whatever kind of experiment you do, if you need a really, really good base pressure, oxygen-free environment, then you have your limitations with a scanning electron microscope. So we have attached a mass spectrometer and we measured the composition of the gas that you have. When you pump down the vacuum to vacuum level, you still see that there is hydrogen, basically water, nitrogen and oxygen inside the chamber. This is a limitation. For many experiments, I would really love to have a UHV level base pressure. And from there on, I could then introduce my gases and study something under very well defined conditions. Another thing that is not really trivial is when you do heating experiments inside the microscope. You can buy a heater, but then there is always the problem that the heater usually is hotter than your sample. So when you cook a milk, for example, on a stove, and the stove is hot, heat goes to the pot, and in the pot is the milk. So the milk is colder than the pot, and the pot is colder than your stove. And we did lots of experiments where we were interested in catalysis, but our heater was hotter than the sample. Lots of chemical reactions take place there. That's one of the issues that is not trivial to overcome. And especially when you have nasty gases in your chamber, the heater can easily corrode and get damaged. Then another thing is when you heat something, you're often also interested in the temperature. Now, how do you measure the temperature for powder very precisely? That is not easy. So we have usually thermocouples that we attach as good as we can to our samples, but then it really depends on how well you can really put your thermocouple onto your sample. And we did some experiments to just estimate how accurate are our temperature measurements. And I have here some videos where we heated up little pieces of aluminum and we put them down onto the heater with some mechanical force, and we measured the temperature the melting temperature. And you will see in this video at one point it gets liquid, and we measured the temperature where it gets liquid, and then we mounted the thermocouple. So here we measured that the aluminum melts at 840 degrees C. You see that nicely in the video when it suddenly changes the shape. That was at around 840 degrees C. And in the same aluminum, different experiments, again aluminum, different particle, we heat it again, and we just had this time the thermocouple mounted somehow differently. And in this experiment, it seemed to get liquid at 550 degrees C. So you see, just depending on how precisely you locate your thermocouple, how good the mechanical contact is between the sample and the thermocouple, you can really create very different readings of your temperatures. So when you want to be accurate, the precise measurement of a temperature is not trivial. Here you see the actual melting point is actually at around 660, so we got quite huge deviations. So these are two limitations, but still it's a friendly instrument, and it works very nicely. So I would like to show you some things about the setup that we have used in Berlin and now also use at ETH, and then I will show you some examples of what you can do. So here's again the setup. So you have the column where the electron beam is generated and focused towards the sample. The passage first through vacuum, then there's some differential pumping apertures and the vacuum level degrades. So you have good vacuum in the column, and then stepwise it gets worse until you reach a certain pressure in the chamber that you can set. We have actually played with these pressure limiting apertures, and we did experiments up to 1 bar in pressure. So this is really crazy. So in principle, you could, during the experiment, open the door and just see if everything is looking well. You would get exposed to some X-rays probably, but you can really work in a very large pressure range. The gas is introduced at some place, either locally feeding directly onto the sample or just introduce it to the chamber. And then we have also a sniffer that goes to the mass spectrometer just to see what's going on. So this is how the microscope looks like. We built a bunch of like mass flow controllers, so we could dose, purge, and whatever gases that we wanted into the chamber. This is the heating stage. You see when the sample is hot, you get a lot of infrared light out and also some thermally emitted electrons. And then we had also here a mass spectrometer to analyze the gas phase. And I just show you some simple experiments that we did. One was that we wanted to try to grow some nanowires. So we had a powder here of cadmium sulfate and zinc sulfate that we just a physical mixture mixed together. Here you can see from the color which is which. So the green ones are zinc sulfate and the pink ones is cadmium sulfate. And then we just heated that up in the microscope under a basically hydrogen atmosphere. And then it was quite beautiful because we could see the growth of these beautiful nanowires, and we could actually study a bit by directly visualizing it. We could study what kinds of processes lead to the branching of these wires. So you see there's a wire growing, and at one point there are like sub-wires growing. And here's another video where you can see that. So there's the catalyst particle is a silver particle, but during growth sometimes this catalyst particle loses some parts, and they can then remain on the rod that is growing. And when these remaining parts migrate to the surface, they can induce additional branches of this nanowire. So it's a beautiful study. The only drawback of this study was that is something you should consider when you do in-situ SEM. Don't use too much material. So we loaded a lot of sample inside, and this all evaporated, and the chamber was so dirty that my student had to clean the microscope for several months until we could continue with other experiments, because it was really horribly dirty. This growth that you see here is a vapor liquid solid growth. So there's a vapor phase because of the vaporization of the cadmium sulfate and the zinc sulfate, and the vapor then condenses on these silver nanoparticles, and then from there you have a vapor liquid solid growth. Just because this is what you see in the SEM, and there was a recent nice paper. Would like to show you something similar, because I just love these results. Let me show you this on the next slide quickly. That is some group that has recently published something. They did something similar in the TEM. Just want to show you the difference. The TEM is really amazing. This is a gallium arsenide wire. This is also an in-situ video, similar process, also vapor liquid solid growth. And this is now atomic resolution. Of course, you cannot compare that, right? So this is very beautiful how this nanowire grows, and you can look it up in this Swiss Reflectors paper. They have several videos here, and they just recently published another paper where they actually can control the structure from word side to the other structure during growth. I know this was just a side thing. I want to show you another example. Graphene was already discussed today during some presentations, and I want to show this because I'm absolutely fascinated by the high sensitivity of the scanning electron microscope. It has extreme surface sensitivity. So we were studying graphene growth, and you know that usually you grow graphene by chemical vapor deposition on some metal catalyst. So normally people have a quartz tube, they heat it up to like 1000 degrees, and they have a catalyst, often it's copper foil, and then they introduce a hydrocarbon hydrogen mixture. And then, you know, you don't see much, this is very hot and shines bright, and so you grow, and after growth you study what comes out. And we did this in the microscope. So we heated copper, platinum, nickel, different metals in the microscope to 1000 degrees, introduced hydrocarbon and hydrogen. And then we really could see at 1000 degrees the formation of graphene. And graphene, as you know, is a monolayer of carbon. At 1000 degrees, the metal surface is so hot that you emit a lot of thermal electrons. So there's a lot of background signal. And from all this background signal, I initially didn't believe that we would be able to see the contrast modulation by a monolayer of carbon. But then we did this experiment, meanwhile we did many. The first thing that we need to do is to clean the catalyst surface. So it's a metal, in this case we used platinum. And just the cleaning alone is something beautiful to watch. So we start with a polycrystalline, I mean, it's always polycrystalline foil, but the foil was initially quite dirty. And you see in this video, this is at like 800 degrees in hydrogen. You see the beginning that the surface reconstructs. You see beautifully how the surface cleans up, how some grains, low energy grains, grow, other grains disappear, so you have some abnormal grain growth. And we did such cleaning processes for many, many hours, cycling a bit the temperature and also the gas phase composition to really get rid also of dissolved carbon that comes from the bulk to the surface during the annealing treatment. And then once we have a clean surface, we can then in the microscope zoom in into any grain that we like, and then introduce hydrocarbon and hydrogen. So hydrogen was always there during annealing, but then we introduced ethylene in this case. And what you see in this video is the growth of graphene. This is the first gray level that you see is a monolayer of graphene. You see how different islands are forming, and then there's a coalescence into a monolayer film. And at some places, I have indicated this here with arrows, you see the nucleation of a second contrast regime. There's a bit darker contrast, that's the second layer. And in some other regimes, you actually see the growth of multi-layer graphene. And that was quite amazing because we're here at around 1000 degrees and we see monolayers of carbon grow in real time. And you can study, for example, how graphene multi-layers form and build up. And we have some very nice results that I hope will be soon published here about the add layer formation. And the crazy thing is that we can, in the SEM at 1000 degrees, distinguish the contrast change for each individual layer up to like 7-8 layers in the contrast range that we have available. So it's really an atomically sensitive tool in terms of the coverage of a surface. It is, SEM doesn't look like an atomically sensitive tool, but in terms of the lateral stacking on graphene, it is really atomically sensitive. And then I would like to show this example to show you that you don't always need a TEM to study things that are related to atomistic processes. We have here graphene islands, a big one and a few small nuclei. And I will run the video and you will see how these individual islands all coalesce together to form a single or a polycrystalline film. And I just do that now. You see that these islands grow and there are some points where they meet, the concave angle, but then it grows nicely into a beautiful hexagonal shaped thing. And we studied this growth very precisely, especially how this concave angle turns into convex angle. With this concave angle, and then it actually, it's really lacking behind in the growth, so this concave angle fills up, the concave angle fills up very fast. So it's starting far behind, but it finishes off very fast. And by just looking at this, also we don't have atomic resolution, but the time is our friend. So we have this additional variable of the temporal evolution. We could actually really study what happens during growth when this concave angle is getting filled up very fast, and how this concave angle that is formed by the zigzag edges of the two approaching grains is changing. And we actually understood that it is during the growth where you have the nucleation of a new row all the time, that the kink formation energy is minimal here in the concave corner. So it's easiest to attach a carbon atom right here in the corner if the two domains are co-oriented. So if it's really uniformly oriented graphene that merges, then you can easily attach a carbon in this place here. It's the easiest place to attach a carbon atom. And then once you have attached this carbon atom, you can fill these two positions with the next carbon atoms. And when you proceed like this, you actually form a specific growth front. It's the fastest growing growth front that has the highest kink density. It's this green one that comes at a certain angle. And with this one, you just grow very fast. And we did some image simulations, DFT calculations, and here are the simulations of what the experiment shows. And it all fitted precisely. So what I want to say is that we have in the stacking atomic resolution, but if you look at the dynamics of the temporal evolution, you don't see atoms, but you can look at the dynamics of the formation of something and then draw back conclusions about the atomistic processes. Another thing that I like a lot about the SEM is you can zoom out, you can look at different regimes at the same time. So what we did here, we have a polycrystalline platinum, and we look at different grains. And by just running the reaction of graphene growth, you see some grains are very active, like this one. This is the first one that grows graphene. It spills over to the next. And the other grains are not active. We have to increase the hydrocarbon chemical potential in order to nucleate there as well. So we can in situ, in real time, judge which surface of platinum has the highest catalytic activity for graphene growth. And you can then, with electron backscattering mapping, you can assign these orientations of the different grains, and you can then plot over a large area activity structure correlations. Yeah, and then just one final example on this, and then I'll stop with SEM, is the surface sensitivity was even higher than that. So I showed you we can see single layers of graphene. And here on the left side, you see graphene grown on copper. You see these dark islands as graphene on copper. And the funny thing is, we took out this sample, and a few days later, we put it back into the microscope. And then we realized that on some grains, the graphene is dark still, and on other grains, the contrast has completely changed. This is another example. The graphene is everywhere, but on this twin here, the graphene has dark contrast, and on the other side not. And when we heated up the sample, then the contrast of graphene got again uniformly dark. And what we realized by doing some in situ XPS measurements at the beamline, we saw from the XPS carbon KH position that the contrast in the SEM actually changed because the coupling stage of graphene on the copper has changed. The coupling after growth is strong, but when you take the sample out, expose it to air, after some time, oxygen intercalates and the coupling changes. And this change in coupling strengths we can visualize in the SEM and measure by XPS. It's quite amazing. So we have extreme high surface sensitivity, and I will speak about one case where we use this surface sensitivity to study surface reactions tomorrow. So now I don't know how much time I used already. I would like to speak with you about in situ TM. So the SEM I have basically covered a bit, and now let's go to in situ TM, sorry. It's quite amazing if you look at the work of Helmut Ruska. He was the guy who developed the transmission electron microscopy, the instrument. His story is very interesting. So one evening, if you're tired, don't want to watch YouTube videos and stuff, read about Ruska. It's very interesting. So he built this microscope, and just a few years after he got his first instrument running and proved that he can really magnify things more than you can magnify with an optical microscope, he already started to study the next thing. He was curious about introducing gases. So this is one of a drawing of a paper he published in 1942. It's amazing, where he has a scheme on how he had different gas reservoirs and he could feed them into the place in the TM where you have a sample located. This is a scheme. This is how it looked like when they did this in Berlin. This was, he was later working at the Fritz Haber Institute, where I was also working, and you could still see the footprint, basically, of Ernst Ruska in the Fritz Haber Institute. Very interesting story. Anyhow, so he studied already in this early age different gases, and he was also interested in how the presence of gases really deteriorate the resolution of the instrument. So he made experiments at different gas pressure and analyzed how the resolution changes that you can achieve. And now, like many years later, we are still doing the same. So this is a paper published in 2012. That's now a modern environmental TEM. And similar like in the SEM, and similar to what Ruska did, you have a place where you create the beam, you have some lenses to condense the beam or to control the illumination. And then at one point you have the sample. And similar, as I said, to the other instrument in the SEM, you make sure that the beam can travel nicely through vacuum, and only close to the sample there's a region where the gas is present. Sorry. And you do this by differential pumping apertures. And also in this paper, that is like a modern version of what Ruska did, you can see studies on how the gas pressure, depending on the pressure of the gas, you lose resolution. So at the beginning, you have your lattice fringes that is evident from the Fourier transformer. You see these rings and spots. But when you introduce, say, like in this case, 20 millibar, you basically lose all the lattice resolution. It, of course, depends also a bit on the type of gas that you introduce and so on. But if you want to learn about this, just please read this paper of Jörg and Stig-Helwig. And there are also some very important studies that have been done with such environmental SEMs. So this is called, environmental TM. This is really a special TM. It's called environmental TM because it has this differential pumping system here. You cannot go up to infinitely high pressures, so just a few millibars, but you can still get high resolution. And this is one of these pioneering works that was published in 2002 in Science, where they looked at the very important catalyst. It's a catalyst for methanol synthesis. It's usually copper and zinc oxide. And they studied how the different gas compositions change the properties of the particles in terms of shape, for example. Yeah? So you could see different particles adapt to the chemical potential of the environment, and it expose different facets and reconstruct to find a local energy minimum. Yeah? There are different approaches. This is a nice paper I want to show you from Peter Crozier and his colleagues. They also used an environmental TEM, and they made use of the electron beam as like a probe also to characterize and measure the chemical composition of the gas phase. So they have actually concentrated, packed a lot of catalyst. In this case, it was ruthenium nanoparticles on some silica fibers. They had like a foamy structure of the silica fibers and impregnated this with ruthenium nanoparticles. And then they pressed a pellet and made a central hole so that the electron beam can, at least at some place here, still penetrate through. So there's a lot of catalyst, and there's one place where the beam can go all the way through because the beam in a transmission electron microscope needs to go through. So they have this hole here, and they packed both things, this whole pellet here, between two TM grids and put that into the chamber. And the cool thing here is that they use the electron beam not only for imaging, but because the electron beam has to pass through the gas phase, and when it just shines through the hole, the electron beam interacts with the gas molecules, and they can then, by analyzing the energy lost by the electrons when they interact with the gas phase, they can actually study the composition of the gas phase. And this is so beautiful when you look then in the energy loss about how many electrons interact with carbon. Is in the configuration of carbon monoxide or carbon dioxide. These electrons lose different types of energy, different amount of energy, and they could really spectroscopically study how much the CO conversion they had, CO oxidation to CO2, because the CO and the CO2 have different locations in the carbon KH feature. So this is a beautiful example. Again, like in many cases, you have this integral measurement of the gas phase composition. So you know there's, for example, you start with CO at low temperature, and as you heat up in oxygen and CO, you see that CO starts to get oxidized to CO2, and at a certain temperature you have already a lot of formation of CO2. That is integral. That's what you measure with the beam passing through the vacuum, through the hole. And at the same time, of course, you can also image some particles. And then that is very beautiful because you can then correlate catalytic activity with something that might happen to the particles when they are in this gas phase. The only problem that you always have in the microscope is you don't ever see all particles simultaneously. So some particles are in the beam, you illuminate them, the beam is hitting them, there is some interaction with the beam, and you never know the particle that I'm looking at in the electron beam, is it really doing the same as all the other particles that are not exposed to the beam? And in the mass spectrometer, you actually have an integral information. So this is actually a tricky point that we can discuss if you like later. And also this works nicely. These were now two examples of this environmental microscope that have these differential pumping apertures. And if you have a normal microscope without such differential pumping apertures, then you can actually buy commercial holders for in-situ TM. This is basically a TM sample holder that has in the front, where you normally mount your normal TM grid, it has a small nanoreactor. Here's a scheme how that looks like. So you have in the microscope the electron beam, and where normally your sample is, you have this nanoreactor. The nanoreactor is made of two chips, silicon-based chips with a very thin silicon nitride window. This silicon nitride window is really thin. It's an amorphous film, 30 nanometers thick. And you have two of these windows. And these two windows, they basically enclose a volume. In this volume, you have your catalyst particles, you have a gas flow, and you can heat. So you have really a microreactor. You just have your small animation. So this is a TM sample holder. In the very front, in this case, there's a heating chip. So you have the current going through the spirals. You can heat up your sample. And all this is actually microfabricated onto these windows. So it's really a micro electromechanical device, a MEMS device, that allows you to build your little reactor. And I have here just as a size comparison, I have such a heated chip where you have a 4-point, this spiral is conducted by 4 points. You can apply voltage, send the current through, and measure the resistivity so you can get feedback about the temperature. So this is such a spiral, as you see here. There's a gas inlet, the gas passes through over the sample and goes out through the outlet, and then ideally into your mass spectrometer. This is the size comparison with a 1 Swiss franc coin. And I zoom in a bit, so now here you can see the spiral. That's where you have your sample. This is the hot area. And in order to be really homogeneous, you really have to put your sample into the central part. And in this central part of that spiral, and just keep in mind the size, it's really small, right? This spiral is very small. And in the central part of the spiral, there are these very thin electron transparent silicon nitride windows. And actually, you have to have sample on these holes, otherwise you wouldn't see anything. So this is the area where you study your catalyst. And this is quite amazing. So this is the area where the temperature is homogeneous. All sample that is here will contribute to, for example, catalytic gas conversion. Imaging only happens in these holes, but it works. Yeah? So the two windows are shielded, packed together. There's an O-ring isolating that gas atmosphere from the vacuum in the column, and this works. This is just, yeah, it's a bit complicated, the whole setup. You can disassemble it, exchange all the parts, and it's really an assembled nanoreactor for in-situ electron microscopy. When you buy such a system commercially, you also get a gas feeding station, so you can control the type of gases that you send through. You can control the temperature and gas pressure. We built such a system in the past in the Fritz Haber Institute in Berlin with some gas filters, because when you want to do atomically clean studies, you also need to make sure that your gases are clean. So we had gas filters and everything. And yeah, this was home built, but this was working so well that the company then solution-based their design on the prototype that we built in Berlin. So anyhow, then you can do such things like what is shown here. So we were growing in situ some carbon nanofibers. We had some catalyst particles. We introduced hydrocarbons, and then we grew these carbon nanoparticles. You can carbon nanotubes, and you can observe while the growth and so on. But we also were always interested in catalysis. So we wanted to know when we do something in the reaction, when something changes, how long does it detect until the gas molecules that change, maybe because of a chemical reaction, can be detected with a mass spectrometer? So we did some kind of tests. So this is these carbon nanotubes. We introduced oxygen, and then we've quickly heated up. And in oxygen, of course, the carbon burns away, and we create a lot of carbon dioxide. And then we were looking at the mass spectrometer and watched and watched and watched forever until there was a CO2 signal. The time response was really horrible because we had long tubings and long distances and so on. Meanwhile, it is possible to get a response after like 10-20 seconds. So if something happens and the mass spectrometer reacts immediately because we have changed the dimensions of the whole thing. And this allows you then really to see something, and at the same time, or basically just with a time delay of like 20-30 seconds, to correlate chemically what has happened to the gas phase while you see something happening in the picture. Oh, these are just some pictures of the setup. There are different companies. I don't want to make advertisement for any of the companies, but I showed you so far a dense solution, and there's also a similar system from Protochips. They have a slightly different philosophy in how they provide the gases, how you mix the gases, but both systems work really nicely. You can not only do in situ experiments in gas phase, but you can also do just simple biasing experiments where you can just apply an electric field or a voltage drop across your sample. You can combine electrical experiments with heat, so you can do some thermal electric measurements, electrothermal and so on. But then you can also do experiments in liquid. This is something that we just recently started. It is extremely amazing because electrocatalysis is quite important, and you can sandwich your sample, and you can really then send I think I have an animation in a later slide. You can send liquids through and do electrocatalysis, quite amazing. And with such in situ setups, you can heat your samples up to more than 1000 degrees. I'm sorry, at pressures up to 1 atmosphere of gas, everything well controlled, and you can do simultaneous imaging and mass spectroscopy. Yeah, this is the setup for liquid cells. So you have the chance to even send liquids through, and then you can apply potential. And you have a working electrode that you see down here. Let me just maybe, yeah. You have like a working electrode where you have your sample, and then you have a reference electrode and a counter electrode. So you can do real electrochemistry. That is quite amazing. And there are some studies where they have really managed to plot cyclovoltammetric curves. So they vary the potential between the electrodes, and they can look at how the current evolves in different directions depending on the cathodic cycle. And you can simultaneously image your sample. But as you can imagine, I told you, electrons are strongly interacting particles. You can see single atoms in the ideal case. But when the electrons have to go through the top membrane, through the liquid, and through the bottom membrane, there's a lot of volume where the electron beams get scattered, and you lose a lot of resolution. So sadly, in situ liquid electron microscopy, the resolution is really dim. It's a fact, and you cannot do much about it. And this brings me to the next point. Electrons are strongly interacting particles. They are beautifully suitable to study single atoms. But because they are strongly interacting, they are interacting with the gas phase or with the liquid as well. And this can create a bunch of artifacts. Yeah? You can send the electron beam through your liquid, and you make radiolysis. You can send them through a material. You can make atomic displacement. The electron beam, it deposits heat. You have lots of charge building up. Charge attracts cracked molecules, and you get contamination and lots of such things. And this is really something that everyone who does electron microscopy should always be aware of, that the electron beam is not innocent at all. Yeah? So this is something very important. This is also very important now with many people doing structural biology, studying proteins and soft matter. And luckily, we have now very good direct electron detectors. We can take pictures with just a few electrons per square angstrom in the total dose and so on. So, but if any message of this presentation is important, then that you have to be careful with electrons and beam-induced artifacts. Not only with electrons, also with X-rays, you can do that. Let me just show you a video. This is an amorphous material. It's a precursor that we studied. It's a precursor that contained phosphorus, calcium, oxygen, and so on. And just by looking at this amorphous material in the electron beam, we saw that some part of this amorphous material left the compound, and the rest started to assemble nicely into beautiful first small nuclei, and then there's some kind of oriented attachment and stuff, and calcium carbonate growing. This is very fascinating to watch, but I can tell you this is all induced just by the electron beam. Yeah? And I proudly have put one video once during my PhD onto YouTube, and it has now already, I don't know, more than 1,000 views. And you see here a bismuth particle doing beautiful dynamics. And at that time, as a young PhD student, I thought I found a working catalyst, but in fact, this is just the electron beam heating up a bismuth particle, and it's like rearranging constantly. So these are electron beam artifacts. These are always there, and they get even worse when you have a liquid, like electrolyte or a gas phase, so you do gas phase chemistry. Just to show you this, for example, if you do anything in a liquid like water or something, the electron beam interacts with the water molecules. You create solvated electrons, OH, OH3O, whatever, different types of charged species and fractions of molecules. And the crazy thing is that each of them has a different lifetime, each of them has a different diffusivity, so you can really change locally, and also with a gradient, the pH. And people have published studies where they, depending on the dose rate, they can get the pH in one direction or in the other direction. They can nucleate particles or dissolve particles. There's lots of chemical complexity in that, and this is something you should take into account. I have here some things. I don't know if I should provide the slides in the end of this conference, but you can look this up. But it's just the message is the same. Be careful. Beam damage is always there. It depends on the nature of the material, on the thickness and the energy of the electrons, of course, and the amount of electrons you deposit per time per area, and many things. So I come basically to my conclusion. The limits of in-situ electron microscopy. First of all, I would say in the SEM, you have lots of possibilities. The limit there is the resolution. It's not a TM, it's an SEM, but you have a lot of space. The limits there is maybe that you have a bad definition of the vacuum because it's not a UHV machine. In the TM, you have much higher resolution, but be aware that when you look at things under reactive conditions and so on, atoms are moving pretty fast. So often the high resolution doesn't really help you because things are moving too fast for detectors to be able to follow them. And that is one limitation, the temporal resolution of our instruments. And then artifacts, size constraints. Yeah, these are the main limitations, but it is possible to study a huge variety of things. It's a quite amazing technique, and some of them I will show tomorrow in my presentation. So here, conclusion, the challenges that we have are related with the nature of electrons because of their strongly interacting nature. The challenge is also related with the fact that microscopes are looking only at a small portion, so you need to be aware that you have to always try to context embed, so to look at things locally, but also try to embed it in a larger context. So don't just look at atoms, look also at different scales, also look at complementary methods like spectroscopy and so on, in situ X-ray diffraction, in situ UV-Vis, in situ Raman, whatever you can get. Yes, then there are challenges that are related with oversimplification. Often we try to do something in situ, but because we cannot do the real experiment at 40 bar pressure and whatever, we try to do simplifications, and often simplifications can be misleading if you oversimplify. And then another thing that is quite challenging when you do in situ electron microscopy, we have no cameras that can take several hundred pictures per second. So during my PhD, I started with negatives, and after a good session, I had like 20 negatives to study. But now we do several terabytes per session, and I don't know how to analyze this data anymore. So this is another challenge. We need to start dealing with big data and machine learning and so on. I think I come to an end. If you want to read more, or I'm always here, you can always write me an email if you have any questions, but there are review articles, there's beautiful work, there are in situ movies, and it's a big and beautiful field. I think with this, I stop. I want to thank you for your attention, and I'm available for questions.
Thank you very much. We are open for questions. So if someone has a question, you can use the blue hand in the participant list, or you can use the chat if you want. No question. I have a question regarding the graphene on polycrystalline platinum. You show a video.
Yeah.
Could you show this video again, please?
Yeah, 1 second. I just try to go back to that video. So here, this one?
Not this one, the next one. The polycrystalline platinum, I guess.
Ah, okay, yeah, this one, yeah.
This one. Is this video versus temperature or versus time?
So the video is running at a constant temperature.
Okay.
And the time is running, of course. The video is running here faster than real time. So we have always hydrogen and hydrocarbon. So there's always a competition between a bit of etching and growth. So we can actually, by changing the ratio between hydrocarbon and hydrogen, we can actually balance it such that there is no growth or very slow growth. And so in these conditions, there's very slow growth. You see, down there you see the scan. Each scan takes 35 seconds per single frame. And I'm running these videos as like 20 frames per second. So it's really sped up a bit. The only thing we varied during this experiment is the pressure of the ethylene. So at low ethylene pressure, only this bottom and the left grain is active. And then in the later stage of the video, we increase the ethylene pressure. And when we increase that, then the other grains also started to nucleate graphene. So we only played with the chemical potential of the ethylene.
Okay, thank you. So we have time for another question. No more questions? So in that case, thank you very much for your presentation, Marc.
Thank you.